Earlier we have learned how an electric current is induced by the relative motion between a closed coil and a magnet. Electric currents can also be induced in a closed coil by causing a change in the magnetic flux, produced by its relative motion with another current-carrying coil in its vicinity, or by a flux change produced by the same coil. Let us first understand the experimental setup that helps us demonstrate this phenomenon. The coil on the left is called the primary coil and is connected to a battery. Let the current in this coil be I1. The coil on the right is called the secondary coil and it is connected to a galvanometer. The primary and the secondary coils are placed coaxial and an iron core runs along the axes of the coils. Let B be the magnetic field strength due to the current in the primary coil. When the secondary coil is moved towards the primary coil, the magnetic flux through the secondary coil increases. As a consequence of the increasing flux in the secondary coil, the current induced in it increases as it moves towards the primary coil. Let the current induced in this coil be I. When the secondary coil moves away from the primary coil, the magnetic flux through the secondary coil reduces. As a consequence of the decreasing magnetic flux, the current in the secondary coil decreases. The magnetic flux in the secondary coil, phi B, is directly proportional to the current I in it. The variations of the current in the secondary coil are directly proportional to the variations in the magnetic flux. Thus, the rate of change of flux is directly proportional to the rate of change of current. Let the number of turns in the secondary coil be N. Hence, the net flux change in the secondary coil, N phi B, is directly proportional to I. The term N phi B is called flux linkage. The constant of proportionality M between the flux linkage and the current is called the mutual inductance of the coil. Inductance is a scalar quantity and has the dimensions ml square T power minus 2 A power minus 2. The SI unit of inductance is Henry, named after the scientist Joseph Henry, and is denoted by H. 1 Henry is equal to 1 Tesla meter square per ampere. So far, we have explored the experimental setup with two coils of the same radius placed beside one another. Let us now consider an example in which two coaxial solenoids induce current into one another. Consider two coaxial solenoids S1 and S2 of length L. Let the radius of the inner solenoid S1 be R1 and the number of turns per unit length be N1. Let the radius of the outer solenoid S2 be R2 and the number of turns per unit length by N2. Let N1 and N2 be the total number of turns in coils S1 and S2. Thus, we have N1 is equal to N1L and N2 is equal to N2L. When a current I2 is passed through the coil S2, a magnetic flux is set up within the coil and this flux is linked with the coil S1. Let us denote this magnetic flux by phi 1. Let this be the flux per turn of the coil. Then, the total flux linkage with solenoid S1 is N1 phi 1 equal to M12 I2. Let this be equation 1. M12 is called the mutual inductance of solenoid S1 with respect to solenoid S2. It is also referred to as the coefficient of mutual induction. The magnetic flux is equal to the product of the magnetic field strength into the area. The magnetic field strength B2 due to the current I2 in solenoid S2 is given by B2 equal to mu naught N2 I2. Let this be equation 2. Area of the coil in solenoid S2, A is equal to pi R1 square. Let this be equation 3. Multiplying equations 2 and 3, we get the value of the magnetic flux in the coil of solenoid S1 as phi1 equal to mu naught N2 I2 into pi R1 square. Let this be equation 4. Also, we know that N1 is equal to N1L. Let this be equation 5. On multiplying equations 4 and 5 and simplifying the right-hand side, we get the expression N1 phi1 equal to mu naught N1 N2 pi R1 square Li2. Let this be equation 6. Equating the right-hand side expressions of equation 6 and equation 1 and simplifying, we get M12 is equal to mu naught N1 N2 pi R1 square L. Let this be equation 7. Note that for these calculations, we neglected the edge effects and consider the magnetic field to be uniform throughout the length and width of the solenoid S2. Also, solenoids of equal length were chosen. This is a good approximation, keeping in mind that the solenoid is long, implying L is much greater than R2. Let us now consider the case in which current I1 is passed through the solenoid S1. This current produces magnetic flux, which is also linked with the solenoid S2. Let the magnetic flux per turn linked with solenoid S2 be phi2. Then, the total flux linkage with solenoid S2 is N2 phi2 is equal to M21 I1. Let this be equation 8. M21 is called the mutual inductance of solenoid S2 with respect to solenoid S1. It is also referred to as the coefficient of mutual induction. The magnetic flux is equal to the product of the magnetic field strength into the area. The magnetic field B1 due to the current I1 in solenoid S1 is given by B1 is equal to mu naught N1 I1. Let this be equation 9. Area of the coil in solenoid S1, A is equal to pi R1 square. Let this be equation 10. Here, we assume the flux due to current I1 through S1 is completely confined to the solenoid S1 only. This is because the solenoids are very long. On multiplying equations 9 and 10, we obtain the magnetic flux per turn through the coil of solenoid S2 as phi2 equal to mu naught N1 I1 into pi R1 square. Let this be equation 11. We also know that N2 is equal to N2L. Let this be equation 12. On multiplying equations 11 and 12 and simplifying the right-hand side, we get the equation N2 phi2 is equal to mu naught N1 N2 pi r1 square L I1. Let this be equation 13. Equating the right-hand side of equation 13 and equation 8 and simplifying, we get the expression M21 is equal to mu naught N1 N2 pi R1 square L. Let this be equation 40. Comparing equations 7 and 14, we get M12 is equal to M21. Let M12 is equal to M21 be equal to M, which is equal to mu naught N1 N2 pi R1 square L. Note that the mutual inductance is neither dependent on the current nor the magnetic flux. It is dependent on the geometrical dimensions of the solenoid. This expression is true when the medium within the solenoids is air. If the medium within the solenoids has relative permeability mu r, then M is equal to mu naught mu r N1 N2 pi R1 square L. This equality M12 is equal to M21 holds good for long coaxial solenoids and is far more general. Even though the inner solenoid S1 is much smaller than the outer solenoid S2, calculation of flux linkage with inner solenoid is possible as it is effectively immersed in the uniform magnetic field due to the current through the outer solenoid. Thus, calculation of mutual inductance M12 is easy. However, in this case, it is difficult to find the flux linkage with outer solenoid due to the current through the inner solenoid. This is because the magnetic field due to the inner solenoid would vary across the length as well as the cross-section of the outer solenoid. Thus, calculation of mutual inductance M21 becomes difficult. Let us now take a look at how a change of current affects mutual inductance. Let us consider an experimental setup in which there is a coil C1 that is connected to a galvanometer G and another coil C2 connected to a battery. EMF is induced in coil C1 wherever there is any change in current through coil C2. Let Phi1 be the flux through coil C1 of N1 turns when current in coil C2 is I2. We know that N1 Phi1 equal to Mi2. The rate of change of current is equal to the rate of change of flux. This means that dN1 Phi1 by dt is equal to dMi2 by dt. The EMF induced in coil C1 is given by E1 is equal to minus d N1 Phi1 by dt. This implies that E1 is equal to minus M di2 by dt. Remember, only flux and current change. Hence, M is a constant. This equation shows that a varying current in a coil can induce EMF in a neighboring coil. Let us now solve an example to reinforce our understanding of mutual inductance. A current I passes through the outer ring of two coplanar concentric loops of radii R1 and R2. R1 is much greater than R2. What is the mutual inductance between the two loops? The magnetic field induced by a current I at the center of the ring of radius R1 is B1 equal to mu naught I by 2R1. The flux through the ring of radius R2 is given by Phi21 equal to B1A2. This implies that Phi21 is equal to mu naught I by 2R1 into pi R2 square. Mutual inductance M is given by phi21 by I. On substituting the value of phi21 and simplifying, we get the value of mutual inductance as mu naught pi R2 square by 2R1.